All right, let's get right into it. We're going to tackle a question that, feels a little bit like magic. How does a simple line of code, just text on a screen, make a real-world light turn on? Well, the answer is something called GPIO. It's the essential bridge between software and hardware, and we're about to cross it. So yeah, this is the core idea, right? It really does feel like magic. You type a line of code, something like, GPAI.ODR equals 0x1, and poof, a physical LED lights up. But I promise you, it's not magic. It's actually a really clever system of bridges and gates. And by the time we're done here, you're going to get exactly how it all works.
Okay, so to really get GPIO, we need to kind of rewind a bit and talk about this huge shift in how electronics are designed, this move from being hardwired to softwired. And this right here really shows you what I'm talking about. On the left, that's the old way. Think digital logic design. Every single connection is a physical wire. If you want that circuit to do something different, well, you better get your soldering iron out because you're physically rewiring the whole thing. It's rigid. But on the right, that's a microcontroller. It's basically a blank slate. The connections are virtual, all defined by the code you write. And that flexibility, that's the secret sauce behind, well, everything. Your phone, your smartwatch, all of it.
So the big question is, how does that software actually talk to the outside world? And that, my friends, is where GPIO comes in. Just think of a general-purpose input-output pin, a GPIO pin, as this perfect little translator. It's the physical bridge that connects the microcontroller's brain to the real world of buttons, sensors, and lights. Your code is the boss, and it just tells the GPIO pin what to do. Hey, you, listen for a signal, or you, go send a signal out.
But here's the cool part. A GPIO pin isn't just a one-trick pony. Nope. It can actually wear a bunch of different hats, or let's call them personalities, all depending on the specific job you need it to do.
So you've basically got these four main personalities for any GPIO pin. It can be an input, right, for reading stuff like a button press. It can be an output for driving things like an LED. Then you've got alternate function, which is where a specialized piece of hardware, like a serial port, kind of takes it over. And finally, it can be analog, to read voltages that are constantly changing. Now, for what we're doing today, we're really just going to focus on the two big ones, input and output.
So, how do you actually choose the right mode? Well, it all comes down to solving whatever puzzle your circuit presents. Let's dive in with a really common input puzzle to see what I mean.
Okay, picture this. You set up a pin as an input. It's supposed to be listening. You've got it hooked up to a switch, but right now, that switch is open. So, what's that pin actually reading? Is it a 1? A 0? High? Low? What is it? And the answer is, well, it's neither. The pin is what we call floating. It's basically acting like a tiny antenna, just picking up all the random electrical noise that's flying around in the air. You can see it in that jagged waveform. The voltage is just all over the place. Now, if you're trying to read something simple like a button press, a floating pin is a nightmare. It's totally unreliable. Your microcontroller is just sitting there completely confused with no idea what to think.
So the solution's actually pretty simple. We have to give that pin a stable default state. We need to anchor it, and we can do that in two ways. We can use a pull-up resistor, which tethers it to our positive voltage, giving it a default high state, or we can use a pull-down resistor to tether it to ground for a default low state. Just like that, the pin has a predictable value when nothing's happening. No more floating.
All right, time for a quick pop quiz. Let's say you've got a switch that, when you press it, connects your pin to ground. So, to stop that pin from floating when you're not pressing the button, which setting do you need? A pull-up or a pull-down? Think about it.
If you said pull-up, you nailed it. That pull-up resistor holds the pin high by default. Then, when you press that button, you create this nice, easy path straight to ground. That path is much stronger, so it yanks the pin's voltage down to low. This whole setup, by the way, is super common. It's called active low logic. Okay, let's flip over to outputs. The most common mode you're going to see is called push-pull. Just imagine it has two little switches inside. One connects the power to push the voltage high, and the other connects to ground to pull the voltage low. It's strong, actively driving the signal both ways. Now, open drain is different. It only has that pull switch to connect to ground. To get the signal to go high, it needs some help from an external pull-up resistor. It's a bit more specialized, really useful for things like communication buses where multiple devices have to share the same line.
Okay, another quick one for you. You just want to turn a regular old LED on and off. Super simple task.
What's the most straightforward, efficient mode for the job?
You got it. Push-pull. It's the workhorse for a reason. It can powerfully drive that pin high to light up the LED and then powerfully pull it low to shut it off. It's simple, it's direct, and it's absolutely perfect for the job.
All right, so we've got the theory down. That's the clean, perfect version. But the real world, yeah, it's messy. So let's talk about some of the common glitches and real dangers you're going to run into with GPIO. First thing to remember, a GPIO pin is surprisingly delicate. It can only push out a tiny amount of current. We're talking around 25 milliamps, tops. So look at the circuit on the left. That's safe, because that little resistor is there to limit the current for the LED. But the circuit on the right? Oh, that is a disaster waiting to happen. A motor is super thirsty for current, way more than that pin can ever provide. If you hook it up directly like that, you will absolutely fry the pin, and you might even kill the entire microcontroller.
And here's another classic real-world headache. In a perfect world, when you press a button, it makes one clean connection. But in our world, a real switch has these tiny metal contacts that literally bounce against each other for a few milliseconds. Now to us, that's nothing. But to a microcontroller that's running millions of instructions a second, that bouncing looks like you're mashing the button hundreds of times. It's just chaos.
Luckily, there's a really elegant solution, and we can do it right in our software. The logic is super simple. When your code first sees that button get pressed, it goes from high to low, you just wait. Don't do anything yet. Just pause for a tiny moment, maybe 20 milliseconds, just long enough for all that bouncing to settle down. Then you check the pin again. If it's still low, now you know that was a real press, not just some random noise.
All right, theory time is over. Let's put all these pieces together. We're going to walk through a simple project that uses everything we've just talked about, inputs, outputs, and yeah, that debouncing trick.
So here's our game plan, laid out as a simple state machine. We start with the LED off. We press the button once, and boom, we're in the red state. Press it again, we transition to green. One more press, and we cycle right back to off. Super simple, totally clear, and it just uses one input and one output.
And here's what that looks like in actual code. You can see how all these concepts just plug right in. Look at the setup part. We set our LED pin to be an output push-pull, and we configure our button pin as an input pull-up. Then, down in the main loop, notice we're not just reading the button directly. Nope, we're calling a special function, button pressed debounced. And inside that function is that wait and recheck logic we just covered. See? It all comes together. Okay, before we wrap this up, let me give you a list of the most common mistakes people make. Seriously, watch out for these. Number 1, you have to remember to enable the clock for the GPIO port you're using. If you forget, the port literally has no power and you'll be pulling your hair out wondering why nothing works. Second, always double-check your pin modes. Third, don't forget those pull-up or pull-down resistors for your inputs, no floating. And last but not least, be really careful when you're writing to the control registers. It's easy to accidentally mess up the settings for other pins on that same port if you're not paying attention.
So, there you have it. We peeled back the curtain, taken all the magic out of GPIO, and turned it into a set of practical, understandable tools. You now have the blueprint for how software reaches out and actually controls the physical world. The only question left is, what are you going to build?